So here in section 4.2, we're going to consider something called an edge path or an Euler path. So Euler is the guy that this concept is named after. So let me motivate this with something called the Konigsberg bridge problem. And Konigsberg is a city in Germany that consists of two islands here, and then this is the river that's flowing through. And then there's 7 bridges, one bridge between the islands, 2 bridges on the west island that go to the north shore, 2 to the south shore, and then 1 bridge to the north and south shore on the east island. And so the challenge here is to find a route here that crosses each bridge exactly once. So pause the video for just a second and see if you can find a route that goes through and crosses each bridge exactly once. You can start and end any place you want. So if you were able to find a route, that's actually exceptional because there isn't a route. And to see why, the first thing that we need to do is translate this problem into mathematics. So remember, translation is sort of the big idea from the chapter here. Translate real life to math, solve, and translate back to real life. So let's name the islands A and B. The North Shore, we'll call that C. The South Shore, we'll call that D. So each landmass is going to be a vertex. So we've got, whoops, sorry about that. So we've got A here and B here, and then our North Shore C up there, South Shore D down here. And bridges are going to be edges. So there's one bridge between the 2 islands right there. There's 2 bridges from A to the North Shore C, so we're going to have 2 edges here. 2 bridges to that South Shore D, so 2 bridges or 2 edges here. And then 1 edge from B to the north and the south, so that'll be here and here. So crossing every bridge exactly once translates into using every edge exactly once in this diagram, or tracing. So the question now becomes, can you trace this diagram? Oh, well, let's come back to this here in a second. Let's do a few more examples and we'll come back. So first, let's look at this idea of tracing. So you may have done this before, traced this diagram before. And in fact, why don't you, again, pause the video for just a second and see if you can figure out a way to trace that diagram. So in order to trace this, you actually have to start at A or E, and then you have to end at the other. So for example, we could do this. We could go 1, 2, 3, 4, 5, and then we'll go around the inside. 6. This is not a vertex here. That's a crossing. 7. And then down here, 8, and then we've ended at E. So as long as you found, whoops, I missed a number here. What did I do? 1, 2, 3, 4, 5. There we go. That's a 5. So as long as you have 8 moves, then you've traced this entire graph. Well, let's see what's going on. That is actually related to the degrees of the vertices in the graph. So let's list the degrees of each vertex. So vertex A has degree 1, 2, 3. And vertex B has degree 1, 2, 3, 4. And then C has degree 2. And then D, 1, 2, 3, 4. Remember, the degree is the number of edges that attach to the vertex. And then E has 1, 2, 3 edges attached. So notice here we've got 2 vertices of odd degree. So here we have 2 odds. And this one was a yes, we can trace it. So let's look at a couple more examples. What if we get rid of the roof here on the house? So we've just got this diagram and we want to know, can we trace that one? And it turns out this one you can't trace. Say I want to start here at A. I could, go around the outside here, and then I'd have to go through the middle, but then I can't go back down here and get this diagonal without using another edge more than once. So, and that happens any way you try to go around this. So this one cannot be traced. That's a no. And if you look at the degrees of each of these vertices, they're all 3. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So we've actually got 4 odd vertices there. And then let's look at one more example. Let's take out here the diagonals that go through the middle. So we've just got the square, and we want to ask, can we trace that? Well, sure. Let's say we start at A. We can just go around the edges here. 1, 2, 3, and 4. And we've traced it. So this one was a yes. And the degree of all these vertices is 2. 2, 1, 2, 1, 2, and 1, 2. So this has 0 odds. So if we had 2 odds, notice that the odd vertices A and E, those were the start and the end of our tracing. If we had more than 2 odds, we could not trace. If we had 0 odds, it didn't matter where we start because we could just go round in a cycle. So we want to try and notice a pattern here between the number of odds and whether or not we can trace. And we're seeing here that if you have too many odds, if you have 4 odds, you can't trace. If you've got few enough, so 0 or 2 odds, looks like you can trace. So we want to know, does it happen in general? And in fact, it does happen in general. Let's look at one more example, postulating that 0 or 2 odds should allow you to trace here. So example 2, I've got this diagram, and I want to know, based on the degrees of the vertices, go ahead and list those out, and then tell me, can you trace this diagram? So pause the video for just a second, list out your degrees, and tell me whether this is a yes or a no. Okay, so for your degrees here, you should get 2, 2, 3, 3, 3, 2, 3, and 2. And we see we've got 1, 2, 3, 4 vertices of odd degree, 4 odds. So, and this one had 4 odds, and that was a no. This one has 4 odds. This is also a no. If you try to trace this one, you'd have to start and end at an odd. So like, say we started here at vertex 3. So you could try tracing this. You go around the outside and you're like, well, I don't want to go up here because then I've missed this part. So, well, what if I come down here and then go up? Well, if I go here, I can't go any farther. And if I go here, I can't go any farther. So you're stuck that way. And in fact, no matter what you do, you get stuck somewhere and you miss part of the graph. So that one you cannot trace. However, sometimes when you can't trace, let's go ahead and box in our odd vertices. That's an odd one. This is odd. And this one's odd. Sometimes when you can't trace, you can add an edge so that you can trace it. So for example, if we added an edge between vertex 5 and vertex 7, that's what the V stands for vertex, and the subscript is just numbering those guys. So now these are even vertices. 1, 2, 3, 4, 1, 2, 3, 4. So now we've only got 2 odds. With this added edge, you should be able to trace. So see if you can trace this starting at vertex 3 and ending at vertex 4. So again, pause the video for just a second, see if you can trace that guy. Okay, so here's one way to do this. You could go around the edge to here. Actually, you could actually go all the way around the rectangle here. So you could do 1, 2, 3, 4, 5, 6, 7, and then go down 8, and then you can go out and back, so 9, 10, and then down 11, and end there. Everything's got a number on it, so that would be the order to trace. And in the homework, when you solve and you show a tracing, just number the edges just like this. Put arrows and numbers on them. Got to put numbers, though. I won't know which way to go. So if we added and made 2 odds, then we could trace it. So it looks like if you got 0 or 2 odds, you can trace, and that's actually a theorem. So an Euler path or an edge path, we'll most likely call them edge paths, is just a path that uses each edge, exactly once. So it's a tracing. And the theorem is a graph has an Euler path if and only if, so that's equivalent to 2 vertices of odd or none that are odd. So 2 or 0 odds, you can find an edge path. So let's go back to the Konigsberg bridge problem here. And if we look at the degrees of these vertices, A is 1, 2, 3, 4, 5. So that one is odd. C, 1, 2, 3. That guy is odd. B, 1, 2, 3. That's odd. D, 1, 2, 3. That's odd. So we've got 4 odds. So you can't trace. This one's a no. You cannot trace that one and use every edge exactly once, and that's why you can't solve the Konigsberg bridge problem. You have to backtrack on one of the bridges or one of the edges. So it was easier to analyze here the translated problem, and then we could go back and say, okay, well, this one cannot be solved. You'd have to backtrack one of the bridges. And then you could say, well, okay, if you use one bridge twice, can you solve the problem? And that actually might be easier to do over here. You could say, well, what if we backtrack the bridge in the middle? So that backtracking is an added edge. And then you can solve this. You can actually go out, back, out, back. Let's see here. And, oh, well, maybe that's not quite the way to go. Let's see. Oh, I know. Go around the triangle on the outside. And, let's see. 1, 2, 3, 4, 5, 6. Oh, that's no longer an odd. So we have to actually start at C and D. So you could start here at C. You could go, let's see here. You could go around the outside. And then you could go around here, out, back, and then finish up. So if we add that extra bridge, we actually can solve this. We could do 1, 2, 3, 4, 5, and then out back, 6, 7, and then we're here, and then finish up 8. So you've only used the middle bridge twice. So to translate back, we would start at the North Shore. We have to go to A, which is the West Island, and then D. So we'd have to start here at the North Shore. We go to A, and then we got to go down to D. And then from D, move 3, we're going to B. So we would come over here to B. And then from B, we went to C. So you come across like this. So, and you could continue doing that, and then you get the translated back solution from your mathematics. So translate to math, solve, translate back. That's our theme. Okay, a few more examples here. So Euler paths or edge paths, how do you find them? Well, if there are 2 vertices here of odd degree, then the path has to start and end at one of those. Starts at one, ends at the other. If there's 0 vertices of odd degree, you can start and end anywhere. And then just in general, when selecting a next edge, don't cut off or isolate part of the graph. So for example, in this graph, you've got these edges over here and then one connecting them and then this piece over here. So you want to use up everything on one side before you cross over. So on this one, we scout this over for odd vertices, and I see an odd vertex here, which I'll go ahead and box in. And then I see another odd vertex right here, so the left and right sides. And everything else looks like it's even, degree 2 or 4. So this one, you should be able to trace this. So what if we start on the right side here and end on the left side? So pause the video for a second and see if you can trace this. Okay, so one way to do this would be 1, 2, I'm going to go around the sort of arrowhead thing, 3, 4, 5, and 6. And then we'll go through the middle and over to the other side. So 7, 8. So notice I used up everything here before I crossed over. And then when you cross over, why don't we go around the kite here? So 9, 10, 11, and 12. And now I'll go through the middle, 13. And then I can't go across an end, otherwise I've missed these edges. So why don't I go ahead and do this sort of horseshoe thing, and then I'll finish up. So 14, 15, and then 16, and 17, and we got it. So that'd be one way to do it. And you may have a different solution, and that's fine. Graph theory is one case where there may be more than one correct answer. So you don't have to do it my way. As long as you've got 17 edges numbered, and you start here and you end here, you got it. So let's look at another example here. This is a street diagram. So this is sort of a subdivision. So these are roads here, and then this is an intersection. Now everywhere there's an intersection, it's sort of understood here that there's a vertex, although we haven't actually drawn all the vertices. So here there's really not a lot of translating to do to translate it to a graph. You just have to remember that there's a vertex every time edges cross. These are not overpasses, they're actually intersections. And we want to trace this diagram. So we want to hit every street exactly once. And why would we want to do that? Well, let's say we want to shovel snow, right? You want to hit every street exactly once, maybe exactly twice. So you could go through and do it the order that you find once, and then you can back up. Just do it in the reverse order and you get it twice. Or maybe you want to salt the streets. You want to cover every street, don't want to miss anything. Or pick up trash. There you usually go down one side of the street, so they might want to hit every street twice. Or delivering mail. Usually the delivery carrier will go down one side of the street and then come back down the other side of the street. So if we can do that, hitting every street exactly once, that's more efficient, and that's going to allow us to save time and money. So same strategy here as before, we just got more edges. We want to first scan over the graph and find any odd vertices. So look over that graph. Do you see any odd vertices? I see a couple here and here. They're degree 3. And it looks like everything else is a crossing here or it's a corner, which is degree 2 and 4. So only 2 odds. So we can trace, we can find an edge path. So let's now actually find it. So one of those has to be our start. So let's let that be our start and this be our end. And one suggestion here in finding edge paths here is to look at patterns as you're drawing your edge path. So what I see is like horizontal rectangles and vertical rectangles here. So you might try doing an entire vertical or horizontal rectangle as you try to find your edge path. So go ahead and pause the video for just a second and try and find an edge path. If you get stuck, come back and I'll show you mine. Okay, so I am going to do this vertical rectangle here first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So got that whole vertical rectangle. And now, why don't we go ahead and do this horizontal rectangle? Okay, so 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, and then I don't want to finish up yet because I haven't gotten some of these edges. So here I could turn around and maybe do the vertical rectangle, or maybe do it in the opposite direction here. So 23, 24, 25, 26, 27, 28, 29 there, 30, and 31. And then I don't want to finish up here with those last two edges because then I've missed this rectangle. So from here, why don't we go ahead and do that horizontal rectangle. So 32, 33, 34, 35, 36, 37, 38 there, 39, 40, 41, and now I can go down and finish up and I've got everything. 42, and to the left 43. So as long as you've got 43 edges numbered, you got everything here. All right, one last example and we'll call it a day here. And as you're working on your homework here, show me your solutions by numbering edges, just like I've done here. Okay, that's the easiest way for you to show me your solution, is to redraw the graph and put numbers on the edges. You might want to do these in pencil, or if you're doing it on a tablet, that works, because then you can just use the undo. If you get stuck, then you just go back up a few steps and try something different. So a little bit of it's going to be trial and error here. So if what you do first doesn't work, then back up and try again. So here we're going back to floor plan problem, which is to pass through each door exactly once. So we worked on the translating this problem before. So each room was a vertex here. So you've got A, B, and C. And then the outdoors, we called that O for outdoors. We had D, E, F, G. So let's see here, D, E, F. Let's put G right here. And then the outdoors, we'll label that O. And then each time rooms have a doorway directly adjoining them, we put an edge. So A is joined to B and D. So we got that edge there and that one there. B is joined to A, C, E. So we already got A, C, E. C is joined to B, G, and the outdoors. So we got B, G, and the outdoors. D is joined to A and E. We've already got A, joined it up to E. E is joined to D, B, F, and the outdoors. So D, B, F, and the outdoors. And then F is joined to E and G. So F to E and to G. And then G to C and F, which we've already got. So now we want to solve the problem here and ask, well, passing through each door exactly once, a door is an edge here. So we want to use every edge exactly once. So we want to trace this graph. So how do you do that? Well, you find the odd vertices. As long as there's 0 or 2 odds, you can trace it. If there's 2 odds, one is the start, one is the end. Why don't you pause the video one more time, see if you can find an edge path or tracing on this diagram. Okay, so if you look over this, B is an odd vertex right there, and then C is an odd vertex, 1, 2, 3, and then everything else is even, 2, 2, 4, 2, 2, 2. So we should be able to solve this. So how about B will be our start, and C will be our end. And then let's see, how about we go around this sort of rectangle first. So we could do 1, 2, 3, 4, 5, 6, and 7. And we're back at B. And then go down through the middle, around the edge, and finish up. So this would be 8, 9, and 10. So you might have a different solution than me, but as long as you've got all 10 edges with labels on them, you've numbered up to 10, you have a solution. Okay, so we translated math, we solved it. Let's translate back. So you go from B to A first. So you go B, A, D, E. So you start here at B. You go A, D, and E. From E, you go F, G, C, back to B. So F, G, C, and back to B, like that. And then from B, you go E, outdoors, and then back to C. So from B, you go down through E, then outdoors, around, and back to C. So like that, and we've gone through every door exactly once. So that's the translate back. All right, so you should be good here to try homework from section 4.2. So the rest of the chapter is only written homework. So you'll solve the problem and then take your pics and do file upload. 4.1 is the only one that had Canvas. If you have any questions on section 4.1, feel free to shoot me an email and I will get back to you. Section 4.1 due by midnight tonight. Have a good day.